In this video, we want to use the techniques of differentiation and integration to be able to develop power series for functions that are much more complex than just the basic ones. But before we get into that, we want to try to recognize a sum of numbers as a particular series, whether it's e to the x or cosine of x or sine of x, to calculate the sum of an infinite sum of terms. So here we have this first example. Find the sum of 1 plus 3 over 1 factorial, so on and so forth. Well, a lot of times you can identify what series it is. So first of all, the first step that you want to do here is you want to identify what series is being used. And then the second thing you want to do is you want to identify the x. All right, so what series are we using here? Well, we have 1 over 0 factorial, and then we have something over 1 factorial, then 2 factorial, 3 factorial, and then we have something to the n over n factorial. Now, with a little bit of practice, you will remember and recognize that the summation from 0 to infinity of x to the n over n factorial is the power series representation for e to the x. So we have identified that this series is the Taylor series for e to the x. It's actually the Maclaurin series. Now, what is the x? Well, the x is just the number that's being raised to the n power. So therefore, the sum of all these numbers would simply be e to that x, so e to the third. And so e to the third would be the sum of all those numbers. Now that we've seen it done once, let's see if it gets a little bit easier in this second example. It says find the sum of 2 minus 8 over 3 factorial, 5 factorial, 7 factorial. So we notice that maybe we'll take the liberty of writing 1 factorial here. So if we notice the bottoms, we have a 1 factorial, a 3 factorial, a 5 factorial, a 7 factorial, and we have terms that are alternating in their signs. That looks a lot like the Taylor series for the sine of x. If you remember the sine of x was equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So we have identified the series. It is sine of x. Now, second thing we need to identify is what is the particular x in this problem? Well, you can see the first number is 2, and then we have an 8, so that would be 2 cubed. Then we have a 32, which would be 2 to the 5th. So our x is 2. So therefore, this infinite sum is simply going to converge to sine of 2 radians. In this third example, we have the infinite series 1 minus 2/3 plus 1/4 minus 8 over 27, so on and so forth. And they are nice enough to basically give us the general term. And so hopefully we can recognize this as a geometric series. A geometric series can be written as the summation from n is equal to 0 to infinity of a1 times r to the n. And so we see our a1 is our first term. So that is 1. And what we're multiplying by each time is negative 2/3. That's how we get from 1 to negative 2/3. And it gives us that right there. So that is our r. And it wants us to find the sum. So we see here that the r, absolute value of r, is less than 1. So that means, therefore, that this is going to converge. And it's going to converge to the sum of a geometric series, which is a1 over 1 minus r. So a1 is the first term, that's 1. And then the r is negative 2/3, so we'll put that right there. And a minus is going to give us 1 plus 2/3. 1 can be written as 3 over 3 plus 2 over 3. So we end up with 1 over 5/3, and we flip that and we end up getting 3/5 as our sum. Okay, here in example 4, we recognize from the last video that this is in the form of a geometric series right here. And so remember that a geometric series can be written as n equals 0 to infinity of a1 times r to the n. Our a1 is 1 right here, and our r is x to the n power. So basically, this is x to the n. And so it says give the first 4 non-zero terms. So we will plug in 0, 1, 2, and 3. So when n is 0, we already know that our a1 is 1, so that's going to be 1. When n is 1, you get x to the first. When n is 2, you get x squared. When n is 3, you get x cubed. So here is our general term. And here are the first 4 terms of the series. And then we know that in order for this to converge, the absolute value of r must be less than 1. So our r is x. So x must be between -1 and 1 in order for this to converge. All right, it says use your answer from part A to find the Maclaurin series for f prime of x. And so now we're going to get into using differentiation and integration to approximate certain functions by generating the Taylor series. So in part A, let's remind ourselves what we got. We had f of x is equal to 1 over 1 minus x. This is our original function, and we are going to approximate that. So we're going to approximate that, and this is the whole point of the Taylor series, with these, this general term, the summation from n is equal to 0 to infinity of x to the n, which gave us a few terms, 1 plus x squared plus x cubed. Now it says find the Maclaurin series for f prime of x. So f prime of x is going to be, well, we're going to take the derivative of this. So maybe we'll do that by moving this up to the top and making it a 1 minus x to the -1. And we're going to do the power rule. So that's going to be -1, leave the inside alone, drop the power down, and then multiply by the derivative of the inside, which is -1. So that -1 and that -1 cancel, and we are left with this as f prime of x. And so now we will take the derivative of the general term as well. So that's going to be the summation. And we're going to do the same thing. We're going to move the n in front, take the x there, drop the power down. So we're going to subtract 1 from there. And we will also take the derivative of these terms. So the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. And then if we were to continue this, the derivative of the next term would be 4x cubed. So what are the first 4 non-zero terms? Here they are. What is the general term? It is here, but now let's pay attention to something here. Notice that normally we start our index at 0. But just notice for a second, if we plug in 0 for n, then 0 times anything is 0, and our first term is 1. But if we plug in 0 for n, we don't get 1. So therefore, you must start your index at 1. Now let's see if that works. When n is 1, you have 1. And then 1 minus 1 is 0. X to the 0 is 1. So our first term is 1. And this is going to converge also at the same places when x is less than 1 or greater than -1. Okay, now it says use your answer to part B to find the sum of the infinite series 1 plus 2/3 plus 3/9 plus 4 over 27 plus ... n over 3 to the n minus 1. Now this is where it gets a little tricky here. So notice here that if we look at what we're trying to sum up, we have a 1, we have a 2, we have a 3, we have a 4. We look at our f prime of x. we are using these four terms to approximate this function. Keep that in mind. These four terms are an approximation of this. So look at what we have. 1, 2, 3, 4. So once again, what we need to do is we need to identify what is the x that's being used to get these numbers, similar to what we did at the beginning of this video. Well, if we have 2x here and we have 2/3 here, that means x must be 1/3. Let's look at the next term, 3/9. Well, look at what we have here, 3x squared. So in order to get a 9 on the bottom, that means x must be 1/3. Let's see if we write that out. 1/3 squared, which gives us the 1/9. So we know our x is 1/3. So if that's the case, then we can approximate this. Actually, this infinite series is really an approximation. Watch this. This infinite series is nothing more than an approximation of this function. And if we've already determined that x is 1/3, we can take 1/3 and plug it in here, and now we can get the exact value. So 1 minus 1/3 squared. So it's 1 over 2/3 squared, which is going to be 1 over 4/9. Flip that and multiply, and we get 9 over 4. Part D says to use your answer from Part A to find the Maclaurin series for the integral of 0 to x f of t dt. So let's remind ourselves what we got for Part A. We started off with f of x equals 1 over 1 minus x, and we said that that was equal, or should I say, we are going to use the Taylor series approximation to be x to the n, which gave us a few terms, 1 plus x squared plus x cubed, so on and so forth. Now we want to integrate f of x. So we want to integrate this, which means we want to integrate 1 over 1 minus x, and let's see what we get. Well, we're going to have to do a u substitution here, so we'll let u equal 1 minus x. du equals negative 1 dx, the derivative of a negative x. So du over negative 1 is equal to dx. So if we go back here, we'll have our integral 1 over u, and dx is going to be du over negative 1. We'll pull that on the outside, and we're going to integrate this, and we end up getting negative natural log of u. And u we called 1 minus x, so this is going to be negative natural log of 1 minus x. All right, so now we're going to integrate the general term as well. So if we integrate the general term, that's going to give us x to the n plus 1 over n plus 1. And now we're going to also integrate these first four terms. So that's going to be x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. So here are the first four non-zero terms. Here's the general term, and it converges once again for all x's between negative 1 and 1. All right, in Part D, we found four terms that we could use to approximate the negative natural log of 1 minus x. Let's keep that in mind. These four terms are an approximation of this function. And now they give us this series, and we need to figure out what the infinite sum is. And this is once again similar to what we did at the beginning of the video. We must identify the x. So what is the x? The x, well, let's just see. 1/3 x. 1 over 3 squared, that looks like x is going to be 1/3. So we're going to plug 1/3 into the real function that we're trying to approximate. And so we will get natural log of 1 minus 1/3. So that's going to be negative natural log of 2/3. And then we remember one of the properties of natural logs. We can take the negative from the front of the log and move it to the top and make it an exponent. So that's going to be natural log of 2/3 to the -1, which means flip the 2/3. So your final answer is natural log of 3/2. Okay, it says find a power series representation for f of x is equal to x squared over 1 minus 2x squared centered at x equals 0 using integration. What in the world are they asking us to do here? Well, before we even go into this problem, let's start with a simple observation. Well, if we integrate, let's say we have a function x squared dx, and we integrate that, I think we all know that's going to give us x cubed over 3. Now, to go back to x squared, we would have to take the derivative with respect to x of x cubed over 3, and that would get us, by way of power rule, x squared. We're going to need to use that concept in this problem. We want to integrate the function that they give us, and then we're going to come up with a power series representation for that function that we get after we integrate it. And then we're going to take the derivative of that power series to get back to our original function. So let's see how this works. So the first observation that we need to make in this problem is we need to separate the x squared from this function. And then what we're going to do is we're going to focus on 1 over 1 minus 2x squared for just a moment. So we're going to integrate that. We're going to integrate 1 over 1 minus 2x quantity squared dx. And so essentially we're going to focus on writing a power function for this series right here, this function right here. And then after we write a power series for this one, we're going to take the derivative of it to get back to this function and then multiply it by x squared. So that's where we are headed. So we're going to integrate this and we're going to get u equals 1 minus 2x. du is equal to negative 2 dx. So du over 2 with a negative is going to equal dx. So we're going to plug this in and integrate. So we're going to end up getting 1 over u squared times dx, and dx is du over 2. So we'll put a negative 1/2 out in front of this. So now we're going to integrate 1 over u squared. When we integrate that, we end up getting negative 1 over u. And so we multiply the negatives and they're going to go away. So essentially we're going to have 1/2 times 1 over u. And u was defined as 1 minus 2x. All right, so now we recognize this piece here to be a geometric series. And we learned that in the last video where our a1, let's just circle that, our a1 is 1. And our r is 2x. So we can write this as 1/2, we need the constant out front, times the summation from n equals 0 to infinity of a1, which is 1, so I won't write that, times r, which is 2x, to the n power. So this is our Taylor series representation for this. And so now we will separate this and make it look a little bit nicer. And so that's going to be 1/2, and the summation from n equals 0 to infinity of 2 to the n times x to the n. And then we will recognize that this is 2 to the n and this is 2 to the first. So we have like basis, so we're going to subtract the exponents. So that gives us the summation from n equals 0 to infinity of 2 to the n minus 1 times x to the n. So now this becomes our representation for 1 over 1 minus 2x. And so what we need to do is we need to take the derivative of this to get back to our original function, because remember we integrated this and we need to take the derivative to get back. So if we take the derivative of the general term, well, 2 to the n minus 1 is just a constant because we're taking the derivative with respect to x, so we'll leave that there. And then we'll do the power rule, so that's going to be n times x to the n minus 1. Now we have to remember something very important here. And the last thing we have to do is we have to remember that at the very beginning of the problem, we pulled an x squared out and we focused on writing the power series for this portion. So now we need to take that x squared and actually multiply it in to our result. And so that's going to give us, well, we have like terms there and there. So that means we need to add the exponents together. So that's going to be 2 to the n minus 1 times n, and then times x to the 2 plus n minus 1. So that's going to be n plus 1. These are very difficult and complex problems, and they require a lot of practice. This next example is actually the reverse of the example that we did before. So we need to recognize that if we have a function, f of x equals inverse tangent of 2x, we can actually take the derivative of that, so f prime of x, and we have to remember what the derivative of the inverse tangent is. Well, it's going to be 1 over 1 plus u squared, and u is 2x, so we'll square that and make that 4x squared, times the derivative of u, which is 2. So there's your chain rule. So let me write that as 2 over 1 plus 4x squared. And so notice now that we now have 2 over 1 plus 4x squared is f prime of x. So now we're going to recognize this as a geometric series. And so now we can recognize that our a1 is 2 and our r is, well, let's write this as 2 over 1 minus a negative 4x squared. So that way we can recognize our r to be negative 4x squared. And so now we want to plug that in to our geometric series representation. So a1 times r, which is negative 4x squared, to the n. So now we want to clean this up a little bit and make it look much nicer. And so maybe we will write it this way. 2 times negative 1 times 4, which I'm going to write as 2 squared, times x squared all to the n power. So we're just breaking this part up into different numbers. So now I'm going to pull the negative 1 to the n out front. And then we have 2 squared to the n. So that's 2 to the 2n times the 2 to the first out front, which is going to give me 2 to the 2n plus 1. And then we have an x to the 2n. And remember, this is all equal to f prime of x, or should I say, this is approximating, let me write this in here, summation from n is equal to 0 to infinity. This is all approximating f prime of x. But we don't really want to approximate f prime of x. We really want to approximate f of x. So if we have f prime of x, what do we have to do in order to get back to f of x? Well, we've got to integrate f prime of x. There's the fundamental theorem of calculus part 1. We want to integrate f prime to get back to f. So we want to integrate this general term. We're integrating with respect to x, so that means everything that does not have an x is simply a constant. So we'll write that out. It's going to be negative 1 to the n, that's a constant. 2 to the 2n plus 1, that's a constant. Now we need to focus on integrating this. And we integrate that using the power rule. So x to the 2n, we're going to add 1 to the power, and then we're going to divide by the result after we have added 1 to that power. And we're going to sum that from n equals 0 to infinity. And that is our power series representation for the inverse tangent of 2x. Okay, in this last example, we want to find a power series representation for each one of these functions. And so the first one is pretty simple. We recognize that to be a geometric series, so we'll write it as 1 minus negative x. And so our a1 is 1. We've been through this before. Our r is negative x. So we can write this as the summation from n is equal to 0 to infinity of, well, the normal power function for a geometric series is x to the n. So we're going to replace this x with negative x, or you could think of it as simply a1 times r to the n. And now we're going to break this up as negative 1 times x to the n. And so that's going to give us negative 1 to the n times x to the n. And that is our power series representation for 1 over 1 plus x. Now we want to write a power series representation for f of x is equal to 1 over 1 plus x cubed. Now this is a little bit tricky. So first thing we're going to do is we're going to just start taking derivatives of our original function. So here's our f of x, and we'll take the derivative of that. And by the way, why don't we write this as 1 plus x to the negative 1. We're just moving this entire bottom up to the top, so that way it's easier for us to take derivatives. So we will multiply by negative 1, leave the inside alone, drop the power down, and then multiply by the derivative of x, which is 1. All right, and then now we're going to take the second derivative of x, and now we're going to do the power rule again. So negative 2 times negative 1 is a positive 2. Leave the inside alone. Drop the power down to negative 3. And then if there was something other than x here, we'd have to do the chain rule, but it's just 1 plus x. And so we can write that as 2 over 1 plus x cubed. Okay, it looks very similar to the function that we're trying to write a power series for. However, we have a 1 here and we have a 2 here, so we're just going to divide by 2, divide by 2. So we get f double prime of x divided by 2 is equal to 1 over 1 plus x cubed. And so this is our approximation for f double prime of x over 2. And so now what we want to do is we want to take the general term and we want to take multiple derivatives of that. So our f of x general term is going to be negative 1 to the n times x to the n. Well, if we take the derivative of that, our first derivative is simply going to be negative 1 to the n is a constant. So we'll leave that there and we'll do the power rule. N times x to the n minus 1. And then we take the derivative a second time. And so that's going to be, so we need f double prime of x is what we're going for here. We need to take the derivative a second time. So we're going to take the derivative of this, and that's going to give us negative 1 to the n. And now we need to do the power rule again. So that's going to be the n that was already there times n minus 1, x, drop the power down to n minus 2. And that is our f double prime of x, but we have to divide it by 2 in order to approximate 1 over 1 plus x cubed. Notice one last thing here. We see that our summation normally starts at 0. But we're not going to put 0 here because if n is 0, then that's simply going to cancel everything on the numerator out. And if n is 1, well, 1 minus 1 is 0. That's going to cancel everything out. So the first value of n that we could actually plug in here that would give us a non-zero term is n equals 2. So it's going to be the summation from n is equal to 2 to infinity of negative 1 to the n times n minus 1 x times, or raised to the n minus 2, and maybe we'll pull the 1/2 out in front of the summation, and that is our answer. Now letter C should be quite simple because this function that we're trying to write a power series for looks almost identical to part B, except it's multiplied by an x squared. So maybe we'll write this as x squared times 1 over 1 plus x all cubed. So all we need to do is take the power series that we wrote in part B and multiply it by x squared. So let's go ahead and do that. We have a 1/2 and summation from n equals 2 to infinity, negative 1 to the n times n minus 1 times x to the n minus 2 times this x squared that we're introducing in this problem. Well, we have like bases, x and x. We've seen this before. That means we can add the exponents together. Well, when you add this negative 2 with this positive 2, it's going to cancel out. And so our final answer should look like 1/2 summation from n equals 2 to infinity of negative 1 to the n times n minus 1, and then x to the n power. And that is the answer. These problems are very difficult and they take a lot of practice, and you may see one or two of these on the AP exam.